This is a weekly summary of interesting news that is relevant for my distributed systems lecture at the Eastern University of Applied Sciences in Switzerland. My name is Thomas Bocek, and today we will be discussing 4 topics. The first one, it's the following tweet here. It's about Aave, and Aave is a decentralized lending platform, and here a user attempted to swap about $50 million worth of tokens through the COW swap. The COW swap, it's the following here. COW, or COW, stands for coincidence of wants, and it's an economic concept where two parties, they have the desire for a specific good or service, and this platform enables direct peer-to-peer swaps without needing a liquidity pool intermediary. However, this COW swap falls back to Uniswap, which has a liquidity provider, which has a DEX liquidity provider. We will talk about DEXs and decentralized exchanges in the upcoming lecture starting in September. But for now, this route used a fallback via a decentralized exchange with a liquidity provider, with an automated liquidity maker, and the order was extremely large relative to the liquidity. A quote came back at 99.9% below expected market value, meaning the user would receive roughly $36,000 worth of tokens in return for $50 million. And the interface, they displayed a warning about this extreme price impact and required the user to confirm a checkbox acknowledging a potential 100% value loss. The user confirmed and proceeded. To execute the trade, the system had to convert the tokens through multiple steps, essentially hopping through several exchanges, decentralized exchanges, to get from one token type to the other. And each hop drained liquidity from a small pool and made the price worse. And by the end, the user received around $36,000. And this is why liquidity matters when executing exchanges. If the market does not have enough supply to absorb a large order, the price degrades with every step. And this post-mortem makes clear this was not a protocol level vulnerability. The Aave smart contract worked as designed. The problem was in the application layer, a front-end widget connected to a third-party swap protocol where a user confirmed a catastrophic trade despite warnings. And in response, the team deployed a feature that blocks swaps with price impact above 25% by default, requiring users to manually disable the protection in a settings menu. Word of caution: when you search for COW swap, you get the following result. So this one here may be harmful. This gave me this warning, but I could not spot any malicious activity on this site here. But this may also be that only certain IPs or browsers gets malicious content, but be aware. So here is actually the second link, which is the right one. And here also the third one, it points basically to nothing. So be aware that there are sites that try to impersonate other sites. As I mentioned, this will be a topic for the upcoming lecture series. The next topic is about supply chain attacks, and it's the following article here. This is a reminder to also keep your dev environment containerized. We talked in the lecture about containerization, and interestingly, this supply chain malware campaign, it's called GlassWorm, has compromised over 430 components across GitHub, NPM, and VSCode extension marketplaces, and researchers identified many places where this GlassWorm is active. And the attack works by compromising GitHub accounts and force pushing malicious commits into existing repositories. The injected code uses invisible Unicode characters to avoid detection during code review, and malicious packets and extensions are then published on NPM and extension marketplaces. And what makes GlassWorm interesting is that it's command and control architecture. So instead of using a traditional server that could be taken down, this malware queries the Solana blockchain every 5 seconds for new instructions. The commands are embedded as memo fields in blockchain transactions, and between November 2025 and March 2026, there were about 50 such transactions, mostly updating the payload URL. And this makes the command channel practically impossible to shut down. You cannot remove data from blockchain. And once instructions are received, the malware downloads a Node.js runtime, runs information stealer targeting cryptocurrency wallets, credentials, SSH keys, access tokens, and the campaign, as I mentioned, is self-propagating. Stolen developer credentials are used to compromise additional repositories and packages, spreading further through the ecosystem. The next article is about protocols. It's the following here, very interesting article. Here, the N0 team announced NOC, a quick implementation in Rust with full quick multipath support. Previously, their network stack managed multiple paths, relay direct UDP below the quick layer, which had no visibility into them and required hacking around congestion control resets on path changes. And with multipath, each path is a first-class quick concept with its own congestion state. The transport layer knows about all paths and tracks congestions independently of the path. And since I wrote my own protocol, it's called QOTP, to learn about all the interesting details about protocols. I have prepared QOTP for multipath, but implementation will become complex, and I try to keep it as simple as possible. QOT currently supports multi-homing but runs congestion control at the connection level. And to make QOTP true multipath, I would need to split the connection state into pair path instances. Otherwise, a lossy path would throttle a clean one. This would be manageable, but what if the paths have different latencies? So solving all these details adds a lot of complexity, which I didn't manage to implement yet. I'm trying to come up with a simple solution, but I didn't find any yet. The next topic is about AI. There are 4 articles that can be split into 2 topics or 2 points. And the first point is that using LLMs is a skill and it's easy to fail at. It's the following article here. This article describes what happens during load coding sessions with AI when the developer gets tired. Their prompt gets worse and worse. Prompts produce worse code. Slow feedback loops make it even worse. And if every attempt takes 15 minutes to test, context fills up and the AI starts losing track. And the authors advise, if you are not confident in your prompt, stop. Invest time in making the feedback loop fast so you can iterate quickly. And the other article, this one here, describes a specific failure pattern. The AI makes a bad decision early on, builds on top of it, and eventually gets stuck in a loop where each fix breaks something else. And the way to avoid this is to stay involved in every decision above the function level and not let the AI make architecture choices on its own. The second point is that AI doesn't remove the need for engineering skill. In this article here, the author makes the point that writing code was never the difficult part of building software. The difficult part is deciding how the system should work, how the pieces fit together, and making sure the code still matches the original plan and the system can grow. AI lets people produce more code faster, but that just means things go wrong faster when nobody is paying attention to the design. Then also in this article, going back again here, this author shows this from experience. The author uses one model for planning and a different cheaper model for writing code, with other models reviewing the result. The process works well, but only because the author makes every design decision and catches bad choices the AI makes. When the author works on a project where they do not understand the technology well enough, the code quickly turns into a mess that AI cannot fix. And the last article looks at this from the other direction. Some people suggest that instead of writing code, you should write a detailed specification document and let an AI agent generate the code from it. And the idea is that writing spec is easier than writing code, so this saves engineering effort. OpenAI's Symfony project is an agent orchestrator that claims to be built this way or to help in that way. The repository contains a markdown specification. The article looks at what is actually inside the spec and finds it is full of database schemas, retry, backoff formulas, concurrency, control logic, and in some places literal pseudocode with function definitions and state variables. And the problem is not that the spec contains code. Specs sometimes include reference implementations, and that is normal. The problem is the claim. The whole point of the spec-driven approach is that writing the spec should be less work than writing the code. But if the spec itself reads like code, then you have not reduced the work. You just have written the code in a different format. And even then, the author tried generating a project from the spec and it still did not produce a working implementation. So the spec was nearly as detailed as the code and it was still not enough. And this brings me to the following comic here. So we see here the date. It's from 2016, but still highly relevant. Here we have two developers. Someday we won't even need coders anymore. We'll be able to just write the specification and the program will write itself. And then the other says, oh, wow, you're right. We'll be able to write a comprehensive and precise spec and bam, we won't need programmers anymore. Exactly. And do you know the industry term for a project specification that is comprehensive and precise enough to generate a program? No, code. It's called code. So in the end, it's just another abstraction layer. That's it from my side. See you next week.